Let's look at another example with this rotational kinematics. A disk initially rotating at 12.6 radians per second is slowed down with a constant angular acceleration of magnitude 4 radians per second squared. The first part, how much time does the disk take to stop? All right, let's go through the same process as we did above, identifying what is given to us. A disk is initially rotating 12.6 radians per second. That's going to be omega. And then it tells us it's slowing down with a constant angular acceleration of magnitude 4 radians per second squared. Here's the thing to be careful of. It's slowing down. So that means we have to take into account what direction things are happening in. Is the acceleration in the same rotational direction as the current angular speed? And the answer is no. Remember, if things are slowing down, the acceleration's acting in the opposite direction. And so we just need to keep in mind that when we're actually putting in numbers, we need to use -4 radians per second squared in our kinematics so that we do actually end up with an object slowing down. And then the last thing, how much time does it take the disk to stop? And so that means that the final speed is 0 radians per second. And then we are looking for time. So going through our kinematic equations, this is going to be a classic first equation case. Omega equals omega naught plus alpha t. The final speed is 0. The initial was 12.6 radians per second, then plus -4 t. All right, a little bit of algebra, add 4t, divide by 4. We get t is 3.15 seconds. So it takes just over 3 seconds for our disk to stop rotating. We'll go ahead and continue on here since this is related to this question. Through what angular displacement does the disk rotate during that same time? All right, so everything we highlighted from before still applies. The initial, I should have written omega naught, sorry about that. Omega naught is 12.6 radians per second. The angular acceleration is -4. The final angular speed is 0. And now we know the time. So really, we could use any of our equations that have angular displacement delta theta in order to solve for this. I just chose to use the second one here. So delta theta equals omega naught t plus 1/2 alpha t squared. We're solving for delta theta, so putting in everything we do know, 12.6 times 3.15 plus 1/2 times -4 times 3.15 squared. All right, and then we can just enter that into the calculator, and we end up with 19.8 radians. So over this 3.15 seconds, the angular displacement is 19.8 radians.